This is video 3.2. It deals with circuits. So we're over here, and our yellow oval here tells us that electricity transfers energy is the key idea, and that's especially true of this particular section. Circuits are all about transferring energy. So here we are then, circuits. The key idea here is components. What do they do? How do they control the flow? So we've got things like switches. We've also got sensing, meters. Well, there's two, ammeter and voltmeter. Resistors in various different forms, and we need to know about combining them. We're also going to be representing the behavior of components in graphs. Now over here we've got the more theoretical side of things, the relationship between these various different parts. Now in red, across the center here, we've got the three key ideas: energy, charge, and time. So charge just means electrons, energy means energy fairly obviously, and time we understand as well. So this should be the easiest place to start. Let's hope so anyway. So if we combine the idea of energy with the idea of charge, we get the idea of voltage. So how much energy is every electron carrying? Charge per time is current, as we can see here. So how fast is the river flowing? How fast are the electrons, or how many electrons per second do we have? Voltage can also be thought of as push, and this can be thought of as flow. So how hard do we have to push to get a certain flow? And that tells us the resistance, the strength of the obstacle we're facing. And then finally, we've got two ways of calculating power. Power is energy per second, so we can have energy divided by seconds here. And we'll see how voltage and current together can also equal or allow us to calculate power. Finally, over here we've got different types of circuit: series and parallel. So here we are then. This is really the heart of the topic. So if you get this clearly in your head, you can't go far wrong. Now on the left hand side here we've got an analogy. There's lots of different ways of trying to explain electricity, and this is one. So we can think of this as a sort of a toy where we're lifting marbles up, and they fall down these steps, and then somehow we have to lift them back up, and we have to put energy into them to lift them back up. Now obviously circuits can be lots of different shapes, but we've modeled this one to be the same as the marble example here. So what the cell does is it lifts them up, in essence. It adds energy to them, and as they go around the circuit, they drop down. We actually talk about voltage drops. So some of the energy is being used to light up this small bulb. Here we're going to have a bigger drop to light up this bigger bulb, and then the electrons go around again. So crucially, the electrons aren't used up in the same way that marbles aren't used up. We're just adding more energy, and they're delivering the energy as they go round, and we call that voltage. Voltage, the energy difference, or the height they fall through, is the voltage, the energy per electron that they're losing. So here we've got the same idea again, the idea that the current, or the electrons per second, doesn't change wherever we are. They're not used up, they're not created, they are just a delivery man. We can think of it like a bicycle chain, but because it is like a bicycle chain, we need this closed loop. As soon as there's a cut here, everything will stop flowing. They can't keep moving round and round. So now we have a little bit of a complication, but hopefully it will help. We don't actually talk about individual electrons very much. We don't say, oh, there's so many electrons flowing per second. And the reason for that is there are so many of them. So this is a typical value here that we deal with. So it's the order of a billion. So it's just awkward to keep saying a billion. So it's the same story with the word year. Imagine we had no rotation on our planet, whatever, and all we had was seconds, which is approximately a human heartbeat. Now, the age of a human wouldn't be very easily measured in seconds, even though we're only dealing with tens of millions here. It would be awkwardly large, and we have all sorts of words for time, months, fortnights, and so on. So hopefully you can see it's essentially the same problem. The numbers are awkwardly large, so a word is needed for a large number, and in the case of electricity, that word is COULOMB. So it's named after a French scientist, and this is the value he came up with. So we're representing that here. There's not really a dotted circle around them, obviously, but we are trying to represent them. It's approximately 6 billion, so Each of these is a billion billion, so we've got these 6 red dots in this envelope to give us the idea of a coulomb. So here we see how some of these different concepts which we met are related. Now, there are quite a lot of formulas in this topic. You can see across here all these different formulas. Some of them are a bit pronounceable. Quit, ver, piv, ipt, not quite as pronounceable. But yeah, you just have to go away and learn them, unfortunately. But let's have a look at what they are. So this is what we saw at the beginning. Energy, time and charge are the sort of founding ideas, and we combine those ideas. So here we're combining time and charge to give us the idea of current. How many coulombs per second? So we've just met the coulomb. How many coulombs per second? But it's really still just electrons per second. And here we have voltage, probably one of the hardest ideas in physics, because it's combining the idea of a joule, which is quite abstract, and the idea of a coulomb, that's also quite abstract. But that's what it is. It's a joule per coulomb. How much energy is every coulomb holding? Power we've also discussed. Joules per second is the easy way of describing it, but because it's so important, it has its own unit, the watt. And finally, we've got resistance. It's an ohm. Omega is a Greek letter, but it is volts per amp. How hard do you have to push to get a certain flow? So let's look at our first equation then. Quit. So this is saying if we know how many coulombs per second and we know what the time is, we can work out what the total number of coulombs is. So if you think of cars per second, we've got 10 cars per second, and we look at it for 3 seconds, we know we'll have 30 cars. So it isn't any different from that, apart from this idea of a coulomb, that it actually holds more electrons. So to repeat, obviously they're not in little neat envelopes. We're just trying to show that conceptually. So these coulombs are flowing past a particular point, and it could be 10, it could be 100. In this case, it's a half per second. And if we consider 10 seconds, we would have 5 coulombs worth of charge. Now, if we want to, we can convert that back into electrons, but as we said, the numbers would be large. So here we've got a more static situation. We've got 4 coulombs here. Each of them is 3 volts, and that's the amount of energy, so 3 joules per coulomb. So the total amount of energy here is 12 joules. So charge times potential difference equals energy transferred. Now here we've got power. Now there are 2 ways of describing power. Either we can use the normal units we'd use in the lab, so joules per second or watts times seconds, which would give us 36 million joules in this case. Now in a domestic situation where you're running lots of appliances for many hours, you don't really want to be ending up with such large numbers. So what we use instead is kilowatts, and we use hours. Hours is a more normal unit of time to describe time in a domestic situation. So the physics is no different. Energy still equals power times time. We're just using different units, and we end up with this slightly unusual unit, the kilowatt hour, but it can be translated back into a number of joules. It's 3.6 million joules, but it is actually more useful in this context. So here we have one of the more complicated formulas to really get your head around, which is power equals current times voltage. So here we think of a nightclub or a soccer stadium or something like that, and we've got a certain number of people paying their admission. They're all paying £5, and we've got half a person per second, or something equivalent. It could be 100, but we're just showing half a person per second here entering the ground. So energy is represented by money. The person represents a coulomb or an electron, if you want to think of it that way. And finally, we have power is energy per second, or money per second. So here we can see it in a more realistic situation, although it's still quite conceptually difficult. So here we've got the coulombs arriving. Here each coulomb has 5 joules of energy, so we can work out energy per second here, can't we? How much energy is arriving per second? Same idea here, slightly differently represented. So we've got a large current here on the top section, smaller current here, and here the yellow indicates the low voltage and the red indicates the high voltage. So if we have this one here, high voltage and high current, that's going to deliver lots and lots of energy per second. It's going to have a very high power. So if we increase V, we increase P. If we increase I, we also increase P. That's what we're saying here in essence. Now a little bit of shuffling here, combining these two formulas, PIV and VER, which VER will come on to in a second, but let's just show it here. If we substitute this in again, we get IIR, which we can tidy up to I squared R. They won't expect you to derive this formula, but it can be quite useful, particularly in when we look at the national grid. So let's have a look at where this formula VER comes from. It's one of the most classic formulas. It's actually quite difficult to get your head around it. What it's saying is that current is controlled by two things in essence. So voltage is the push, so the more we push or the higher we hold our water reservoir, the greater the flow will be, and the equivalent of that is increasing the push, the energy, or the energy per coulomb or per electron that we're getting from our supply. So energy per electron, if we increase that, we're going to get a greater flow, a greater current. And on the bottom of the equation then is resistance. So we can adjust resistance in our variable resistor here, but in our water analogy here, it's like pinching our rubber tubing. So the more we pinch the rubber tubing, the greater the resistance and the less the current will be. So there's an opposite relationship here, and one increases, the other decreases. So this is known as Ohm's law, and it's represented by the formula V equals IR. So moving on then to series and parallel circuits. So a series circuit means the components are in a series, one after the other, and there is only one series. Now here we've got a voltmeter. Now it's not really part of the circuit. It's just measuring or interviewing the electrons here and afterwards to see the difference. So this is not part of the circuit. Here we truly have two paths that the electrons can take. And that's why this is a parallel circuit, because this line is parallel with that. When we make them in reality, often the wires are a bit messier, but the essence of it is there is more than one path, and that's what makes it a parallel circuit. So here we have a number of different components that we can look at, or we need to know something about. So we've got switches, open and closed, which control the current in one way. Light dependent resistor, which we'll look at more in a minute. A diode is a one-way gate. An ammeter is in the circuit there. It's really in the flow, in contrast to a voltmeter, which we've just said stands outside and just compares. There shouldn't be any current flowing through it. So we've got a lamp here, a thermistor, which we'll look at in more detail in a second, a normal resistor, a fuse, which we'll look at in another video, variable resistor we've just talked about, a cell, and then if we combine cells, we get a battery. So let's have a look here at what happens when we change the voltage. So for a normal resistor, we can increase the voltage and the current will increase, but at a set rate. We get a linear relationship or a directly proportional relationship. R doesn't change, the resistance is constant. Now that is not the case for a bulb, which forms part of a lamp. So here, at very relatively low voltage, the tungsten ions, what the filament is made of, have some heat, but they're sort of gently moving around, as you can see, and the electrons can move past fairly easily. Over here it's much hotter, and this is a bit like people trying to run through a corridor when there's people dancing as opposed to people standing still or almost still. So it's much harder, there are many more collisions, and therefore the resistance is higher, and we can see that in the slope of the graph compared to here. We could calculate the resistances using a triangle if we wanted to. Moving on then, we've got here two resistors that are similar in that they both respond to the amount of energy they get. So first of all, the thermistor. So when it's cold, the electrons don't want to come out to play, and they don't want to form part of a current. But we give them a bit of energy. You can see here that the yellow atoms have released quite a few of the electrons, and current flows more easily. With the light dependent resistor, the story is the same. The only difference is the energy comes from light rather than heat. So we have this characteristic graph. We get greater temperature and we get less resistance. Stronger light, we also get less resistance. we can represent this on a graph. We've got the resistor, we've got the changing resistance here. We saw a version of this just a second ago, but if the voltage was reversed, we would get the opposite story here. We'd get the current going in the opposite direction. Now diodes, we mentioned previously, after a short while, about half a volt, which you can't see on here, they will behave like normal resistors, and they will increase their resistance in a regular linear way, but in the reverse direction the resistance is infinite, which is very useful in certain circumstances. So now we're looking at combining resistors. Now if we just combine them in a series way, we are adding constriction upon constriction. We're only making it harder for the electrons to get through. So think of a hose. If you have someone standing on a hose and someone standing on the hose a bit further down. However, if we combine resistors in parallel, what we're doing is we're creating an extra path. Now it may be a very poor path, it may be a massive resistor, but it's still better than nothing. So it's going to be slightly easier for the electrons to flow, so the overall resistance of this section of the circuit will decrease, because, as we keep saying, we've added a path. Now finally here we've got some, or nearly finally, we've got some equations. As I said, there is quite a lot of equations. Again, I won't go through this in huge detail, but you can see that using our IPFAS2 we can get a good range of answers. So we talked about sensing. We can link some of these things together to make sense of the world. So here we've got light, dependent resistor, we've got a thermistor. So if either of these things are the case, and it's not raining because we've got a rain sensor here, then our motor here will put our laundry out. So this is a particularly complicated example, but you get the idea. We can combine these sensors to make sense of the world and do something useful. So finally then, an example of something useful is a thermostat, which uses a thermistor to respond to temperature, and what we're saying here is that the share of resistance will vary as the thermistor increases. It will take a greater share of the resistance. It will also take a greater share of the voltage. So a voltmeter across here will have a different readout or a different output or a different out depending on what's happening. Now this variable resistor here can be adjusted to change the threshold. So if this changes, the fraction of resistance that this one represents also changes. So the thermistor itself changing, it's pretty obvious that that affects the voltage across it. It's less obvious that a resistor somewhere else has that effect, but it is nonetheless the case. So if temperature goes down, resistance will go up of the thermistor, and the V out will also increase, and that might typically switch a heater on.